Hello everyone and welcome back to yet another video. So in this video I just want to first tell you that I have made around 47-48 minutes long video in which I covered everything that I built from scratch, and the computational graph which is currently working for us. Unfortunately, during the video I just wanted to have some more audio gain, and I had just raised the volume entirely, and it turned out like distorting the entire audio, so I couldn't get that back. So I'm just gonna have a quick recap of the previous video, what we have done and what I'm gonna do next. So without the further delay, let me just give you a quick recap of what we have achieved so far. So let me just pull up the directory right now. So where we are, so I'm gonna go to the folder, and I'm gonna xdg open for you something called graph final.png, right? Okay, so this is actually our computational graph so far for the forward pass for our transformers framework. And if you can see over here, we have successfully built this graph for the forward pass, and which is working totally fine. It doesn't have any missing link, and it has, it's keeping the record, keeping the identity, keeping the operation names for each and every tensor we've used so far. So starting from here, which was actually our initial tensor, to all the way up. So this part is very you see slice operations, because we slice the heads of the entire tensor, slice the heads out of the big tensor, and you just create dk dimension tensors. So this part is like multi-head attentions. You can have an idea in multi-head attention. We slice the heads, and we have transports right through our operations, and we have lots of stuff going on here. So operation times means tensor multiplication, division, and soft-to-max. So you can say that this part is basically representing multi-head attention, right? And then we have this part, which is actually we just concatenate the multi-head attention output to some tensor, and then we just go perform layer norm on that, which basically normalizes your tensor, your data. So normalization, it basically helps your algorithm learn fast, right? So this is actually the whole purpose, to make things smooth, to normalize the spikes and peaks, and get everything in a specific bound that we need, right? So this is actually our layer norm. You can see operation expand columns, operation subtract, square, mean. So these are the steps that we do in the layer norm, right? So this was actually multi-head attention, and this is a square layer norm, and then followed by feed for neural networks, because you can see there's something called ReLU, which is the activation function for hidden layer, and times, operation, add, scale. So you see every single tensor. So this is something called if you can see my cursor, so this is something we called operation nodes, right? And the operation nodes, basically they take tensor and they do some operation and give you some new tensor, right? So these are actually operation nodes, and the tensors that are generated without any operations called leaf nodes, right? So which don't require grids most of the time. Sometimes they do require grid, right? Okay, so this is actually the multi-head attention, layer norm, feed for neural network, and then again a layer norm, and then we are here, right? We are here, are at our final loss. So this is the entire graph. You can see I've just pushed the changes on my GitHub. That's called PyTorch. You can search that out. So I coded a lot for 47 minutes. I fixed the bugs, each and everything, but unfortunately I lost the video, and I just wanted to give you a recap of this is how the graph is working now. And now, guess what? Once the forward pass is done, we've built the computational graph, everything is working fine, no missing links. Now it's time to backpropagate, right? So we've already started work on that, and in this video we are going to be working on backpropagation, right? So we just quickly pull up tmux over here, and split the screen horizontally, and here we'll be using our terminal, and here we'll be using our codes, right? So I'm gonna open something called main.c. And also one thing that I want to show you, which is very cool, right? Which is very cool. So you've seen the graph. Now you know that we have some sort of operations going on. In case if I want to show you something here as well, let's just build the graph here and run graph validation. This is actually graph validation. Okay, so this will have, you have seen the visual interpretation of the graph, and now let me just show you that how many nodes are there, how they are getting created. So in order to, in case if I just run this, vim run, and this one, right? Perfect. So let's just try to run and see what happens. Multiple definitions. Okay, where have we defined this? Tensor C, and let's just comment this out for a second. Uh, and main. Alright, so we don't have multiple definitions of main now, and in case if I run it now, so in total we have 114 nodes, right? You can see here 114 nodes. Null parents, we don't have any null parents, which means that every tensor that is created from some operation has some parents. So it's keeping a track of every single tensor with the parents, and also the operations means backward functions, and which we'll be using extensively in backprop. So you want to keep track of every single operation, how it is being created, and you just traverse. When you traverse back, you sort of have a record. You need to have a record of this backward function, right? For example, let's say if we have some tensor addition method which takes two A and B tensors and add them both, right? So in order to backpropagate, we need to have a copy, not exact copy, gradient copy, you can say, or backward copy of that specific function, which tells backpropagation how to calculate backwards. So here we've learned a very important point, that backward propagation is not a one single recursive backward call. It's basically a node-wise recursive call, and node-wise recursive call means we keep track of how the node is created actually, and how we need to backtrack or backpropagate for that particular operation, right? So basically it's the collection of the entire backward. The generic backward is the collection of a small sub backward propagations operation wise. This was the idea that I just wanted to convey. Alright, so visited nodes are 114, and still they're very low. This is just a prototype, mind you. In actual transformers we have tens of thousands, but we'll create that. It's just a matter of adding more layers, and by layers you mean that more heads maybe, or data units or something like that. So we don't have null parents, we have no null operation. Null grids found one. At one place we find null grid, and we need to try that out but for now we're just totally fine. So this is actually lost. So forward passes are doing fine, and now we need to traverse, right? Okay, so let me just, okay, so that you can see. Okay, so this is what, let me just go to main.c, and for now I don't need this. Okay, I don't need this. I'll be working totally with the tensor file, and I'll be testing and doing whole lots of different things, right? Okay, so let's just go to tensor.c, and okay, now here's the thing. Let me just show you something. Should I pull up? Well, you know what? Okay, can I just explain over here? Okay, so let's just say we have some loss which is getting computed using some operations, right? And the first operation is, let's say the loss is mean squared error. Mean squared. So if you have ever done some machine learning, you know that what is actually a cost function, what is actually a loss function, right? So it is basically, it calculates the loss. It calculates the difference between the target and actual values, right? So it gives a sense of how much away, how much far we are with the actual values, and then we sort of use gradient descent to get closer and closer and reduce the gap between the cost and where we are actually, right? So mean squared error. So mean squared error is basically, we do lots of different things. We do like let's say pred minus target squared, and then we take the mean of this. Yeah, mean of this entire thing. Mean. Alright, so basically that's how we calculate the mean squared error, divided by size sometimes, right? So now you see when we calculate mean, so first step, let's look at it step by step. So the first step is subtraction, difference, for which we have a method called tensor subtract, which is subtracts what, pred minus target, and since it takes the square, so we don't have to be worried about which comes first and which comes at the end, right? And then we have something called square, and this is, we can do like tensor square is square, right? And let's just say it takes the square of the difference, right? And then we have third step is taking mean, right? Taking mean. So then we take the mean of this squares, right? Let's say if we have, like, for example, if we have a square for the shape, let's do it here. So a square has shape, a square shape would be, and a square shape means after getting this square, after doing the square of this, we have something called 1632. That's it. That's the shape that we have, right? And then we have mean. Tensor, we have a method for it called tensor mean. We pass in square here, and it gives us mean. But here the thing is, like, we have shape of the mean is, shape mean would be like what? So it basically takes the row wise mean, right? And by row wise we mean that let me just show you here. Okay, so it takes row wise mean, and row wise means that we have, let's say 1632 will shrink down to 16 cross 1. So it takes row wise means, right? It takes the sum and divides it with basically the column's length, right? So in that case, when it takes the sum, this dimension, the column's dimension, will shrink down to only one atom, because it will later divide this with the number of columns, and then we'll be having this shape 16 cross 1 after the mean, right? Then we do a one important function that is expand columns. So we have a method called tensor expand columns, which takes what? Which takes this mean and it returns expanded columns. So let's say I think I'll have to pull this up. Slow music. See, I was actually doing some research on how to get back my audio, but I could not. So sketch. Let me bring this sketch over here. I think you can see this. Are you able to see this yet? It seems like you're able to see this, and let me just zoom in a bit. All right, so what we have is, so after mean, where's the pencil? Okay, so after mean, we have something called let's say 16, 20, 19, whatever, these are the values, 100 maybe. Okay, so the dimension would be like 16 cross 1, that is rows cross 1, right? And then we expand the columns, so that we have final shape 16 cross embedding dimension, which is 32 in our case, right? So we'll be having 16 all the way till here. We'll be having 20 all the way till on this 31st index as well. And let's not call it 31st because you get confused. 20, and then we have 19 all the way here. So this will have shape 16 cross 32. So after taking the mean, we expand the columns in order to match the dimensions because it cannot work otherwise, right? So let's go back. So here we have expanded the columns, and now we have shape. Shape is 1632. And that was actually basically the output of this particular loss, right? So we have loss equals some output of expand columns method. I hope you are understanding, right? So loss is basically the output of expand columns method. Now here's the thing. We need to start back propagation from the end, right? So first of all, what we're going to do this, we have some loss matrix, some loss having shape equals 16. Let's call it sequence length embedding dimension, right? embedding dimension. So in my case, that is 1632, right? So this is the case. All right, so we need to backpropagate, and we need to backpropagate operations wise. Like I've mentioned earlier, that I cannot write one generic backward method which just magically does the backward operation. We need to specify, we need to check the tensor operation that we've performed on each particular node, and we need to do sub backpropagation, or sub backpropagation would be like complex sub recursive operation to take the gradients of those tensor operations, right? For example, in case, let's just start with the loss. So dl over d loss over loss would be 1. So we'll be starting from gradient tensor shape. Let's say it will have shape 16 cross 32, all ones, right? And then we have inside, we have this. Now see, mean squared error is itself is nothing. We need to pay attention to primitive abstract tensor level operations in order to find the derivative, right? So the last operation that we perform in this mean squared error was actually expand columns. Now we need to take the gradient of this expand column. So we need to have some function called tensor expand columns backward, right? We need to have some function which calculates the backpropagation for this particular operation. And in case if I want to show you something, that's why we've created all these back methods. So see, each and every tensor operation, primitive tensor operation, has some backward function, right, which will be calculating the backpropagation for that particular operation or for that particular method. So here in this case, expand columns backward, we have expanded. So this is actually the same explanation which I just explained to you in much detailed form. So we have something like this, and now the problem is, see, the problem is for tensor expand columns, this function forward, let's call it forward for now. Forward, we have shape equals what? So the output of this gives us 16 cross 32, right? But the loss gradients tensor, let's just copy this, and then we can paste here, and then we can delete this. Okay, and this backward has some member. This basically returns a tensor. Do not confuse, please. So let's just write it here. And okay, so this returns us a tensor with member called grad, having shape equals 1632, which is basically the shape of this forward pass. Now here's the problem. The problem is this will give us, this backward method, this will give us shape 1601. Why? Because the way we compute the gradient for expanded columns, for example, if we expand the columns of some tensor, the gradient is simply the accumulation or sum across the dimension. For example, if forward returned this thing, let's say 1 1 1 1, right? And let's say it's like 2 cross 3 tensor, 1 1 1. Let's say if forward returned me this, because I expanded the columns in order to match the dimensions, the derivative of this thing is, let's say this returns This was some tensor which is returned using the forward operation, and then we have the t dash would be what? The gradient would be simply the sum along the dimension, right? And that would be 3 and 3, right? Right? This is actually the gradient. In simple words, you just, for expanded columns, you just take the dimension, you just sum them up, and you just return the output. But here's the problem. This stores grad member dimension as what? 1632. And this has actual dimension after taking gradient equals as, can you guess? Yes, that's right, 16.1. Now, here's the problem. How can we match the dimensions? Because always remember, whenever for the forward operation, if you're trying to find the gradients, these both should have the same dimension, right? The dimensions cannot change, right? So I was just stuck in here. And let's just try to do this. Let's just try to work on it, and let's see if we can solve this, right? Okay, so I guess will this work? Oh, really? Alright, so this should work, I guess. Vim run. So this is actually a problem. So you understood the problem. Now we are trying to resolve this problem. Let's see how we can solve it. Okay, so I'm gonna run this and reference to main. Yeah, undefined reference to main. Okay, so like what? Yeah, I'll comment this thing out. Ooh, alright, what is this? What is this? What's going on here? And what? Let's bring this entire discussion inside it. Can we do like this? Yeah. Okay, so we are able to run this, and now you see the seg fault error. This is because I was trying this previously, and I was hoping that if this can. Ooh, what is this? Oh yeah. So I should not like remove this. Okay, fine. So this is something. And now if you can run as no seg fault work, it doesn't work basically. So we have require squared. Okay, fine. So let's just go to this tensor expand calls backward. Okay, let's see how we have implemented this. Okay, and one thing that I can do here is so let me just see how have I implemented this forward pass. So we have tensor columns, and this basically takes the output columns, right, and expands along the dimension of the columns, right? So the output shape is fine, but the gradient of the output shape should not be like out shape, should not be equals to out shape. So this will have different shape, and let me just try to do this in case if this worked. Let's just see. So grad shape is something like this, and this is rows, and this will have only what? Oh, one, right? Because we need only one column, and this is not this is grad, and this is also grad, and now this should have grad shape, right? And now if we just go to main, and main, let's just copy this thing from here and put them all here, yeah, like so. And then we have tensor external columns, and let's just see this also at what actually are we doing. Tensor backward, and what this does basically, yeah, so this basically sums over the row pointer and sums over the row pointer and columns equals 1, and apparently it looks fine, but let's just try to run and see. So we have vim run, and yeah, let's see what happens. So seg fault, segmentation fault, okay, back, expand the columns backward, and let's just see if we can print the sum. Where exactly is this seg fault happening? Is there anything wrong with the X shape and X grad data? Okay, so we have X grad, X grad. Tensor. Alright, so X is basically, what is X? So let's just dissect it a bit. So X is mean tensor, and output is expand column function output. So this output uses uh, back chain rule to update gradient of input, which is x, right? And x grad data plus r times I think the shape is not correct, maybe. Um, is this shape correct or not? Segmentation fault. What exactly is wrong here? Expand columns, right? Expand columns. Expand columns. Okay, so this is um, expand columns. Where is expand columns? Okay, so it won't work because uh, y squared equals true. Yeah, so I think we need to have some tensor like this, right? And um, this will have shape this. Yeah, 16 1. Let's consider this a mean tensor, just one tensor before this expand column, and uh, then um, can we draw its diagram over here? So I think we have um, alright, so I think we have this. This goes here, expand, and then we have some laws. So dl by l will be 1, so this will have outgrad. That's the confusion, I guess. Grad equals 1, expand columns, and then we have mean here, which has rows and 1. So using this outgrad, we can populate this thing. Is it correct? That's the question. Um, so let's just try to implement this thing. We have expand columns right here, and we don't want metadata. And this is our X, and okay. Okay, so this is actually the main tensor. Yes, that's correct. And now, what we want to do is no. This is going to be X shape 1 columns, and this is not a main tensor. That's the confusion, right? That's the confusion. This is basically X parameter that we are passing here is tensor that is output from forward pass. Okay, now the mystery has resolved, right? Very simple. Just columns sum plus equals what? So yeah, out data, let's see, right, and after this loop what we do here is we just append these two parents, right? So not so tensor m p equals x parents 0, if not p return. Yeah, this is actually what we need to do, and just this is going to be p so let me just confirm one thing. Yeah, r would be sum, right? Okay, so let's just see this backward method, and hopefully this will do the job for us. Okay, so this is our actually expand method, right? And first of all, we just grab the parents, right? And we know that this is basically a expansion. The input is going to be the mean, which is going to get expanded, right? And then we just extracted the parents, and we checked if it's null, then obviously we're going to return out. Otherwise, we're going to parse the rows and columns, and then we'll loop, we'll collect the data, we'll sum along the rows, and we just, pass the p gradient, this sum, and that's it, right? And in case if we run it now, we don't have any segfault errors, right? But this is something. Okay, so let's just see what error do we have. So out data expand column backward. Yeah, this is not out basically, so let's just this is X basically, right? Yeah, so this segfault is now coming from because we are not matching the shapes perfectly, because we, for mean tensor, we have number of rows and columns, but here we are initializing just a random tensor just for testing, which is like this. And let's just confirm one more thing. Yeah, so okay, so expand backward. This should be 32, right? And we need to know, the problem is, see, I'm taking this expand this function just for the testing purpose. I'm taking it as the output, this x as the output of expanded columns, right? And it takes the mean, right? So the x backward function, this should have parent, that is the mean, that has the shape mean equals mean, right? 16 cross 1. But currently it doesn't have any parent that has mean, or in case if you can make one. So let's just say tensor. Let's try this out. So int p parent shape. Let's say this is going to be arena log a, and then times size of teachers. So p shape 0 equals 16, and p, just for the testing purpose I'm doing this, 1, right? So this is now our locally assigned parent, because this is for the testing purpose and we were not assigning any parents. That's why we were stumbling upon this error segmentation fault. And let's see now, tensor parent, and this is going to be tensor create new with a and dimension, and what, p shape. Now let's assign x parents equals let's say p parent 0 parent, right, like so. And let's just see if this works now. Boom. We need to see a couple of things over here first of all. So randomize x should be here, and yeah, tensor, yeah, so randomize this too, so parent, and let's just see, and this also parent also requires grad, so parent equals true. Okay, and tensor metadata x parent, and now let's just try to see what happens now. Parent, what is parent? Okay, so x parent 0 equals parents. P shape parent x 0. This should be a tensor. Boom. What is wrong here? Ooh, yeah. So I'm not actually creating this. I should create this. Arena allocate one time size of pointer, and now okay, so we have defined the parents, we have defined the x, and expand backwards. So there's something wrong with expand backwards now. So expand expand. Okay, so what is wrong here? What is wrong here? X parents. I'm trying to access some memory, which is I'm trying to read from the memory which is not created maybe, or which is out of the bound. So if not parent return. Can we do one more thing here? Parents not found. Exiting. Okay, so what is wrong here? Like, I don't have no clue what's wrong here. Okay, so this is 1632 and this has shape 16.1. So we have parent and we have the data as well. And let's just quickly check this R method. Can I put some extra checks here? So Should this be like grad data? This should not be grad data, this should be data, right? Because we are using the output from forward pass to calculate the backprop, right? But what exactly is wrong? Like, I have no clue what exactly is wrong. Um, columns, R times columns plus C, which is correct. P grad data. Okay, so we haven't. Um, okay, so have we found parent if um um number of parents. Huh. So sum is good. Yeah. So till here everything is fine. Uh, till here everything is fine. And what? P grade and data. Mm, okay. Yeah, so something is wrong here, right? We are able to print this and grade and data. So can we print the shape of this P? Uh, print f, oh, tensor get tensor shape 2D P, and let's just uncomment this to remove the noise, and let's just see. Ah, dear, I commented out the wrong line. Found parent 0. It does not have any parent. What's going on here? And let's just see here. So tensor experiment column has x. So x parents equals p. So let's see if not um parents. Do we have parents here? I mean, what exactly is wrong? I don't think it's that big of a problem, so we can check. Um, we'll also randomize parents and oh man, like look at this. Yeah. So first we need to create this. This should be here. So x parents equals arena allocate, and x has parent is equal to parents, so tensor parent is equals to this, and we've just assigned um, like this should be here, and x. So we have allocated this space, right? And we have um, So parent requires grad equals true. Mm, okay, so we have allocated the space for the parent. We have created parent, and then let's randomize this. So yeah, so this is going to be parent. This should work, man. This should work now. Found no parent. What exactly is wrong here? Oh yeah, so x guard equals new and x shape and that's it. So we'll look in some other session. I am not able to solve this problem. I will see this later because right now I'm just exhausted and this doesn't seem like a big issue. Uh, it's just, it doesn't seem like a big problem, right? So we'll fix that later, and thank you for watching. See you in the next one. Take care.